So let's dive right in. What is a rational number? Well, a rational number is called rational. Again, a rational number is called rational because it can be written as a fraction. I told you that word rational comes from the word ratio. So you could also say it could be written as a ratio. So we have a list of all these numbers up here. I need to know, and please help me out, which ones do you think are rational? Which ones fit this rule of being rational? And go ahead and let me know. Give me one of them. Which one's rational?
3.
Yep, that is rational. We could write that as 3 over 1, so that is a rational number. Give me another one, guys. Log base 2 of 8 is also rational. Do you guys know what that's equal to? That's equal to a whole number. What whole number?
3.
Yep, 2 to the third power is 8. Okay, give me another rational number. Again, our only qualification is it can be written as a fraction. 14, yeah, that is a rational number. We could write it as 14 over 1. It is this whole number, so that counts. -5, that counts as well. Something that can be written as a fraction or can be represented as a ratio. 3 to 1, -5 to 1, 14 to 1. 2 cubed is just 8, so yeah, that is totally a rational number. 2/3, that is a fraction right there, so that is a rational number. We still have a couple rational numbers left. 20/3 is a rational number, and 2.7 is also a rational number. You can think of this as 2 7/10. That is a rational number. We can rewrite it as a fraction.
Are these always rational?
No, there are some that are not rational.
7 over 0 not rational?
It's not. Does anyone have a hint why it's not rational?
2 over 0?
Yeah, our denominator cannot equal 0. So we can't have a denominator equal to 0. So there we were able to write it as a fraction, but never 0 denominator. Okay, what about the 2 that are left? I will tell you one of them is a rational number, one of them is not. Yeah, 3 to the -3rd is rational, which means radical 5 is not. Now, 3 to the -3rd is just 1 over 3 cubed, or 1 over 27, so we can write that as a fraction. But the square root of 5 has a repeating decimal. So I'm actually just going to say, like, any radical has a repeating decimal. And so no fraction can represent that. No fraction represents that. So if we're thinking about rational numbers, we can't have square roots. Square roots, by definition, are irrational. We can't have denominators equal to 0, but otherwise it is a fraction. So let's extend that definition to a rational function. A rational function. So just like in our last module, a function, in this case a polynomial, was x squared, x cubed, x to the 4th, x to the 5th. A rational function is just going to be a function that we're writing as a polynomial, or a fraction of some polynomials.
what he had said, right? I mean, okay.
So
But these aren't much, I mean, that's what
our parent function,
when we practice, you mentioned we saw that.
our parent function is just really basically f of x is 1 over x. You'll notice that we have a fraction with variables in the numerator and denominator, or at least a variable in the denominator. So I need you guys to suggest a polynomial for me. So any polynomial. Think back to the last module. I need an example of a polynomial.
Son of Bino makes no freaking sense to me for what John says. What do you mean? Renew lockbox for 6 months, then close or fail for 90.
Okay, an example of a polynomial. Any polynomial you guys can think of. Maybe think about the project you just did, or think about any of the homeworks we've done recently. I need a polynomial.
Are you asking for it in standard form or like a fraction form?
Let's do standard form, just a regular standard form polynomial.
Okay, let's look in the homework. Would x minus 1 squared work?
Yeah, that's a polynomial. So let's divide it by any other polynomial. Divide it by any other polynomial.
Can you do like x squared minus 9 plus 20?
Yeah. So this is what rational functions are going to look like. They will have a polynomial in the numerator and a polynomial in the denominator. Essentially, it is just a fraction of polynomials. So anytime we see a fraction with x is in the numerator, x is in the denominator, that is a rational function. And the main idea here is that it's a fraction, which was the main idea of a rational number also. So we're going to do some operations with these. Some operations, meaning we're going to write these out. We're going to add them. We're going to subtract them. We're going to multiply. We're going to divide. Add, subtract, multiply, divide. Let's start by adding. So adding rational numbers. I'm going to go through the process of adding just plain old rational numbers, and we're going to use that process to add rational functions. So when I'm looking at these two right here, the first thing I know I need to do is find a common denominator. And I'm actually going to multiply each side by the opposite. So opposite denominator. So here I'm going to multiply this one by 3 over 3. And this one I'm going to multiply by 7 over 7. So I'm multiplying each fraction by the opposite denominator. Okay, let's go ahead and do that. And we multiply both numerator and denominator. So 7 times 2, 14. 7 times 3 is 21. 4 times 3 is 12. 7 times 3 is 21. And that was our goal, right? We wanted to create a common denominator. We have a common denominator. So now that we have a common denominator, we're just adding the numerators. So in this case, I'm going to write this step out, but you don't have to. You can definitely internalize this step. 14 plus 12 all over 21. You'll notice that we don't touch or change the denominator. So I'm just going to add a note that we keep the denominator intact. And then we just have 26 over 21. Now, if it was possible to reduce this fraction more or simplify it more, we would, if it was possible. So we always just look as our last step to simplify. So let's run through these steps once more because we're going to try them with functions in just a bit. First, I'm establishing and finding a common denominator. This means I need to multiply each fraction by the opposite denominator to get that common denominator. So I create the common denominator. Then I need to add the numerators. I don't really touch the denominator after that first step. All I do is add the numerators, keep the denominator intact, and if there is a chance, I'm going to simplify. And you'll see that when we're using functions, there'll always be a chance to simplify. So let's try these same steps on the rational function. Same steps on the rational function. Okay, first step is to find a common denominator or multiply each side by the opposite denominator. So I have an x plus 1 on this side. I need to multiply this one by x plus 1 over x plus 1. I have an x plus 3 on this side, so I need to multiply this one by x plus 3 over x plus 3. You'll notice that I'm multiplying by the whole factor, not just, well, this one has an x and that one has an x, so I'm multiplying by 1 and 3. No, I need to multiply by the whole factor. I can't break those factors apart. So that first fraction becomes 3 times x plus 3 all over x plus 3, x plus 1. And that second fraction becomes 4x, x plus 1, all over x plus 3, x plus 1. Now we have a common denominator. That was our first step. Multiply by the opposite denominator to reach our common denominator. So at this point, we can move on to our second step, which is just adding the numerators. 3 times x plus 3 plus 4x times x plus 1 all over our denominator. Remember, we're keeping our denominator the same. We're not even going to multiply it out. We're just going to keep it intact. This is where we get to simplify. Because we have binomials, we have polynomials here, there is plenty to simplify. So let's go ahead and let's distribute the 3 to make that 3x plus 9 and distribute the 4x plus 4x squared plus 4x. But again, we're still keeping the denominator intact. There's nothing to change in the denominator. And as a final step, we're going to combine like terms. So I don't see any other x squareds. All I see is this 4x squared right here. So that's going to be our leading term, 4x squared. 3x and 4x together is going to make our 7x plus 9. And again, keep that denominator. It just kind of tags along for the rest of the ride. So I'm just going to talk through these steps one more time because this a process of addition is the trickiest process. First, we need to find our common denominator, and we're going to multiply each fraction by something that gives us the common denominator. In this case, it was just the opposite fraction. So this one, the x plus 3, got multiplied to both sides, and to both top and bottom on this fraction. And then the x plus 1 got multiplied top and bottom to the other fraction. Once we rewrite our fractions with those common denominator, we can just add the numerators. That's what we did here in this step. We added the numerators. And then we're simplifying it, and we're trying to write that numerator in standard form. I'm going to jot that down. Standard form. Our numerator is in standard form. Our denominator we can leave as factored form. You guys ready to try another one? Okay, this next one, we're going to start with irrational numbers again. So I'm starting with my rational numbers. And this time, I could just multiply this by 8 over 8 and multiply this by 6 over 6, but I think I see a better path. I think I see a simpler path. Does anyone want to suggest something else we could do instead?
8 and 6 have a common factor, which is 2, so we can divide them, right?
Really close. So they do have this common factor of 2. This is 2 times 4, and this is 2 times 3. So I technically don't have to multiply by 6 and by 8. Can't I just multiply by the factor that's missing? I
You
don't.
just get like go to the denominator.
Highlight it.
Yeah, does anyone know what that common denominator is going to be that we're hunting for? We could do 6 times 8, which is 48, but we don't need to go that large. So I could just multiply this one by 4 over 4 and multiply this one by 3 over 3. And then I get myself to that 24 on both sides. Now, you could do it the other way, but I just want to show you a way to keep our factors smaller, because that's going to be really helpful when we start the rational expressions. So this becomes 9 24ths, and this becomes 20 24ths. So the process we did here is called a least common multiple. You don't need to know this word for specifically, but what we did is we found like a smaller number that they both go into without just multiplying them outright. But our first step is still to create a common denominator. In this case, we didn't multiply by the denominators entirely. We multiplied by that least common multiple. Okay, so we created our common denominator. Now we are just adding the numerators. And again, I'm going to write this step out, but you can definitely internalize this step. You don't have to write it out yourself. And if there was an opportunity to simplify, we would. Remember, we're keeping our denominator intact. Scoot this over a little bit. Keep the denominator intact. And if you have an opportunity, simplify. But I don't think this one simplifies. So let's look for this same process on this second example. Again, first step is going to be create a common denominator. And this time I'm going to look for a least common multiple. I'm going to look for maybe a factor they already have in common that I don't have to multiply. And I see that right here. They both have an x plus 3. So I don't need to multiply by x plus 3 to get a common denominator. I can just multiply by the term that's missing. So I can multiply this one by x plus 2 over x plus 2. Because now I have that missing x plus 2. And I can multiply the other side by x minus 1. And now they have all three terms. So I didn't multiply the entire denominator. I just found that one factor that was missing and multiplied the opposite side by, or the opposite fraction by that missing term. So our new fraction is 2x times x minus 1 all over our common denominator of x minus 1, x plus 3, x plus 2, plus our new numerator, 4x, x plus 2, over that same common denominator, x minus 1, x plus 3, x plus 2. So once again, we've created our common denominator. We're not going to touch our denominator the rest of the time. We're just going to keep rewriting it as we go down. And our next step is to add the numerators. So let's go ahead and add those numerators together. 2x times x minus 1 plus 4x, x plus 2, all over the one denominator. And remember, we are keeping our denominator intact. The rest of the problem, our denominator is going to look exactly the same. We're not going to do anything with it. So now our job is to just simplify. Let's go ahead and distribute. And I say just simplify like it's easy. It's not. This will be some of the trickier stuff that you do. 2x times x is 2x squared. 2x times negative 1 minus 2x. 4x times x is 4x squared. 4x times 2 is plus 8x. Again, all over the same denominator. And then our goal is to have standard form in the numerator. So let's combine like terms. I see a 4x squared and a 2x squared. So let's make that 6x squared. And I see negative 2x and a positive 8x. So that would be a positive 6x. And again, we're keeping the denominator intact. So we create our common denominator, we add our numerators, keeping the denominator intact, and lastly, we simplify. So I'm going to skip the slide on subtraction. I will post a solution for it later, but I'm going to skip the slide on subtraction because I want to show you multiplication and division. Multiplication and division are a little bit easier because we don't have to worry about a common denominator. But before I move on to multiplication and division, questions on adding either example 1 or example 2. Okay, let's try our multiplication. So I'm skipping the subtraction and let's go straight to multiplication. If I'm going to multiply these rational numbers right here, if that is my goal, I could just multiply straight across the numerator, right? I could just say, well, 3 times 5 over 8 times 6, that's 15 over 48. Sweet, that would do the job. Multiply straight across the numerator. And in this case, the denominator. But I don't think I'm finished here. I think I would then have to reduce the fraction, right? So I would have to look at 15 and 48 and say, do they have anything in common? Well, they do have something in common. They both have a 3 in them. Do they have anything else in common? They might have something else in common. I have to kind of think through that. If I take 3 out of both of them, I'm left with 5. Help me out, guys. You can reduce these fractions. If I take a 3 out of both of them, what am I left with?
The first one would be 5. And then 16.
Yeah. So and then I would check, can I reduce that further? But we can't. That would be the final answer. But there is another path to take. There is another path to take here, and that's by starting off by reducing the fraction. So I'm going to draw arrows because we could reverse the order. We could reverse the order, and that's what we're going to do on rational functions. So let's take a look at the rational function, and let's try reversing the order where we start by reducing the fraction and then we multiply across. So here I see this rational function, and remember, I'm going to multiply straight across. So I can think of this as one large fraction, because I am just multiplying straight across and multiplying straight across. So let's start by reducing the fraction. Do we see any common factors, meaning factors that are exactly the same in the numerator and denominator? I think so. I think I see an x minus 2 and an x minus 2. Those are exactly the same. We're going to divide those. When we divide them, it becomes just 1. Okay, do we see any other common factors between the numerator and denominator? I don't think so, so let's multiply it together. We're going to multiply straight across, so it's x plus 1, x plus 5, divided by, multiply straight across, x plus 2 squared. Now, because we reduced first, I know that's my final answer. I don't have to look back on it and see is there another factor that can be combined. So essentially, we're multiplying across the numerator, multiplying across the denominator, and reducing, but I suggest you reduce first. First, look for a common factor that you're dividing between the numerator and denominator.
Say,
Mm-hmm.
do you leave it in factored form, or do you have to put it in standard form?
Always leave it in factored form. So there's only one way these problems get trickier, and that is that you would have to factor first. So your first step for all of these problems would be to factor. And what does that mean? You want to actually write it in factored form. So that is the only way these problems get a little bit trickier. Once you factor everything, then you'll have a problem that looks like this, and you can follow this process. So we're going to try one more example, just one last one. This one is dividing. If we look at dividing rational numbers, I learned back in I want to say 6th grade, 5th grade, that when we're dividing numbers, we invert and multiply. I actually learned it as this karate chop move, invert and multiply, and I have never forgotten that sense. Essentially what that means is that when we're dividing by a fraction, we're multiplying by the reciprocal. So I'm going to write that out, multiply by the reciprocal. And that just means flip that second term upside down. So this is still going to stay 3 over 8, but now I'm going to multiply by 6 over 5. And we're going to follow all of our steps for multiplication. So let's start by reducing. Is there anything we can reduce here? Do we have any common factors? Well, I think 8 and 6 have some common factors. I think 8 is 2 times 4, so we can take out that 2 and just be left with 4. And 6 is 2 times 3, so we can take out that 2 and just be left with 3. So I like to reduce first. And then multiply across the numerator, multiply across the denominator. 3 times 3 is 9. I'm going to write that step out. You do not have to write this step out, but just to kind of internalize it, 3 times 3 and 4 times 5 is 9 over 20. And we'll find that we have a reduced fraction already. So let's try the rational function together. Our first step is we're going to change this to multiplying by the reciprocal. Multiplying by the reciprocal. So our first term, x plus 1, x minus 2, all over x plus 2 does not change. But we're going to multiply by the reciprocal. We're going to multiply by x minus 2, x plus 2, all over x plus 5. So now we're just following our steps for multiplication. Let's reduce first. Reduce first. So we're looking for any factors in common between the numerator and denominator. Well, I see this x plus 2 and x plus 2. Those will divide out to become 1. X plus 5, there's no x plus 5 in the numerator, so I think at this point we're just multiplying straight across. X plus 1, x minus 2 squared, all over x plus 5. Now I wrote x minus 2 squared because we had x minus 2 times x minus 2. That is the preferred way to write it. Write it as the two terms squared. And in my mind, anytime we're reducing the amount of things we have to write, that's a win. So once we set up the reciprocal, it is just multiplication. Reduce first, then multiply across both the numerator and denominator.